much. Okay, just share my screen so we can get started. Okay, thank you very much. It's a pleasure to be here, albeit virtually. I hope someday soon we can all get together in person again. And I really welcome this opportunity to go over sort of the grand sweep of my interests over the past decades. To some extent, it looks like a random walk through climate physics, but there are a few unifying principles. And I want to actually say something about what led me from one topic to another and give some perspectives on how I think about climate physics in general. And along the way, I also want to acknowledge just a few of the vast number of people from whom I've learned things, from whom I've learned the things that make my research possible over the years. This is by no means everybody that I've learned things from, but just enough to give you the flavor of how I actually educated myself to be able to do some of this stuff. So the start of how I think about climate problems can be understood in the comparison of chess versus Go. So I think of climate as a problem in physics that's emergent behavior, emergent from relatively simple components. And so in chess, you have complex behavior, openings that people memorize and things like that, that actually emerge from complex rules. You have many different pieces, each which have their own behavior and so forth. We take the game of Go. Let me see if I can get my annotation up here. Yeah, so if you take the game of Go instead, there's really only there are really only two rules. Players take turns putting down either their white piece. Players take turns, the black player and the white player. And the only real rule is that when all the liberties of a group are taken, so this would be an example of a liberty of this black piece, then that group is captured. And from those two simple rules, all sorts of structures emerge. For example, the notion that a group with two eyes, two open spaces, and this white group almost has two eyes, it could easily get two eyes, is alive, nothing can kill it. There's the notion of, say, joseki, which are the patterns that you use to start in the corners, which human players use, but it turns out that the AI computer players have developed a style of play that can actually start in the center and radiate outwards, which no human players really thought of doing, except for rank amateurs who would then get beaten very quickly. You get the ideas of sort of iterative structures. She chose capture ladders and things like that, that either live or die depending on where they collide later. And all sorts of other things. And so all of these complex patterns come out of the most elementary of rules. And let's see, I'm trying to. Yeah, and there's also a very beautiful aesthetic component of Go, the sound that the pieces make when you put them down, the feel of the pieces in your hand, the beauty of the Go board, I think science is like that too. There's at least the kind of problems I like to work on are partly chosen for their aesthetic appeal as problems in science. They like science to have a kind of a narrative arc and not just be a bunch of technical exercises. So what are these basic components of climate science, of climate physics? Well, they're more complicated than the simple rules of Go, but I think they have sort of the same spirit. And so the most fundamental components of atmospheres and oceans are Newtonian mechanics, which is in the form of fluid dynamics, thermodynamics, which is in the form of equations of state, things like phase change, what components are condensable and how much energy do they transport, which all comes from the beautiful Clausius-Clapeyron relation, and things like enthalpy conservation. It's just a restatement of the first law of thermodynamics. And then there's radiative transfer, the transport of energy by absorption and emission of electromagnetic radiation. And the fundamental principle of climate that goes back to Fourier and that determines most of the key aspects of climate and certainly constrains them strongly is the principle that the climate is determined by the requirement that the energy in for example, by absorbed sunlight, has to equal the energy emitted, generally in the form of infrared radiation. Okay, and that is the fundamental principle of climate that underpins almost everything that we do. In some ways, all of climate science it amounts to successive elaborations of this statement that the energy in must equal the energy out, computing the energy out in a hierarchy of more complex models and more rich models. But there are extended components. And here's one I have kind of mixed feelings about, although it's terribly important. Atmospheric chemistry, which determines how the atoms that make up an atmosphere are rearranged into molecules. And given that, say, methane is a greenhouse gas, but other things you can make out of carbon and hydrogen are weaker greenhouse gases, or other places you can put the carbon, makes a lot of difference how your atoms are arranged into molecules. And that's the business of atmospheric chemistry. And this kind of atmospheric chemistry, although it's terribly important, and I've had to deal with some of it, it kind of goes against my general feeling that most of climate is an emergent phenomenon from simple rules. Because although chemistry is governed by simple rules at the base of it, the way chemical networks play out are, to me, a little bit more like a pachinko machine, where you have to know where all of these little pins are and what these little bumpers do in a particular machine to know how it works. This is the reaction network for the destruction of methane. And it's not even the complete reaction network, because it doesn't tell you where the OH radical, which is the workhorse of oxidation, really comes from. So I've tended to avoid working too much on atmospheric chemistry, because I actually find it hard to reduce it down to simplified networks that still capture enough of the basic phenomenon that they're actually worth working on. We're doing a little bit of simplified network work with just hydrogen and oxygen for steam atmospheres. So atmospheric chemistry doesn't entirely fit into my narrative arc for this, but it's important nonetheless. It needs to be dealt with. But then there are other extended components which actually can be captured with fairly simplified models, and then you can work your way up the hierarchy. So you have crustal reactions with the atmosphere, which actually determine, to a large extent, atmospheric composition. Notably, the thing that determines how much carbon dioxide stays in an atmosphere is the silicate weathering process. Carbon dioxide in the presence of water reacts with silicate rocks like basalt to make carbonate, limestone, basically. There are other biogeochemical cycles, including the nitrogen cycle, which affect the atmospheric composition. But given that carbon dioxide in conjunction with water makes up a lot of the greenhouse effect that regulates the climate of habitable planets and even of uninhabitable planets like Venus, the silicate weathering thermostat, which I'm doing quite a lot of work on in my group right now, is really quite important. And then CO2 and other atmospheric components have to come from somewhere. Atmospheres are dynamic entities. They have their source in the original material of the planet, and then later what is outgassed from the mantle. So mantle chemistry, for example, the amount of iron in the mantle that didn't segregate into the core affects the chemistry of what is outgassed from volcanism. And then you also have to have a way in the CO2 cycle, in the deep carbon cycle, to recycle the carbon dioxide you've turned into limestone. Otherwise, the whole planet will suck up its CO2. And if it was a formerly habitable world, it will freeze out, turn into a snowball Earth. And there are different mechanisms of crustal recycling, plate tectonics versus resurfacing with stagnant lid convection. I wouldn't have time to do more than touch a few of the basics of some of these things in this lecture, but it's an extended component that turns out to be at the very heart of what makes a planet habitable and how long it can remain habitable. And then you can go further afield from the planet once it's formed to ask, how did the planet form and how did it get the volatiles that actually ultimately went into making up its atmosphere and ocean? By the way, I should say that as far as my view goes, oceans are just a dense form of atmosphere. And the only reason we actually have a strict separation on Earth between ocean and atmosphere is that the Earth is cool enough that water vapor is not supercritical, so that you have a phase change, a phase discontinuity at the surface of the ocean. If the Earth were at 700 Kelvin instead, then actually water vapor would just continuously make the transition from a gas-like substance to a fluid-like substance without any phase change. And the distinct ocean surface would disappear, but the ocean would still act a lot like an ocean. And the dense parts of many atmospheres, like the dense hydrogen on gas giants like Jupiter and hot Jupiters, in some ways is more like an ocean than like an atmosphere. But by the way, in any event, you have to ask, how do planets get their volatiles? And that comes down to the dynamics of protoplanetary disks, which are hydrogen dominated with some dust thrown in, and the dust is where we come from. And I've learned to think of protoplanetary disks. Actually, I've just written a popularized book in the Oxford University Press, very short introduction series on planetary systems, which covers a simple version of protoplanetary disk dynamics. So I've been learning about that. I've come to think of protoplanetary disks as just a rather funny shaped atmosphere. It has a lot of the same phenomena we're familiar with in atmospheres, like Hadley circulations, Rossby waves, and so forth. But it affects the chemistry and the distribution of the substances like water, carbon, and nitrogen that go into making the atmospheres of various kinds of planets. Now, in the dedication to my book, Principles of Planetary Climate, which Leslie was kind enough to mention, I dedicated it to Arnold E. Ross, who taught us to think deeply of simple things. This was the motto of a mathematics program I started going to when I was about 14. That was run at first Notre Dame University, and when I got there, it was run at Ohio State University for many decades. And in fact, the program still exists 60 years on from its founding. So it was a program that took people from high schools and introduced them to advanced mathematics through number theory. And number theory involves, at its simplest incarnation, the theory of the properties of the integers, 0, 1, 2, 3, -1, -2, etc. But goes from there to generalize to other kinds of integers, like integers on the complex plane, and even generalizes beyond there to a general class of things called rings. And all this proceeds from thinking deeply about very simple things. Number theory is a little bit like Go. You have a few simple rules of arithmetic, and from those few simple rules, deep questions emerge, some of which, like Fermat, took centuries to answer, and some of which still have not been answered. I'll give you an example of one of these. But the 4 years I spent at this program learning number theory and various other kinds of pure mathematics, they have always had a big influence on what on the way I think about science. And the general idea, if you look at the history of pretty much any scientific subject, but atmospheric climate physics in general, is that big ideas come from small models. General circulation models have an important role to play, but a lot of the real conceptual breakthroughs come from small models that you can analyze deeply by mathematical methods. And then you work your way up and you iterate it from there to see how the ideas play out in general circulation models. You go back down to the small models and you converge on understanding. That way. So to give an example of some of these, some number theoretic questions, as I said, questions are easy to state in number theory, and you can understand them in elementary terms if you basically just know about arithmetic, but they can be hard to solve. So an example of an emergent concept, emergent behavior, is that the simple concept of divisibility leads to the concept of prime numbers, and then very deep questions about the distribution of prime numbers, which can lead you very far afield. Some of those questions, like the one relating to the Riemann zeta hypothesis, still are not answered. And some of the answers to the questions require you to go outside the number theory itself into analysis. And that was the case for the role of elliptic curves in solving Fermat's last theorem. So Fermat was solved some decade ago, but many are still outstanding. Many of these simple problems are still outstanding. For example, the Goldbach conjecture that every even number can be written as the sum of two primes. So now I'm going to go through one that actually has a kind of a dynamical systems flavor, which is the Collatz conjecture, sometimes called the 3n+1 conjecture. So you pick a positive and then you multiply it by 3 and add 1. Then you divide that by 2 repeatedly until you get an odd number again. Then you iterate this to create a series. And the conjecture is that no matter where you start, this series always terminates. And you can show that if it terminates at 1. In other words, it doesn't have periodic orbits. It doesn't run away to infinity. It always terminates as 1. So this is a simple conjecture to state. It's even been turned into a kind of a board game, and a little bit like snakes and ladders. And it's unsolved. At least the last time I checked, it was still unsolved. Just to give you an example of some of the behavior. And how it really is a kind of dynamical system on the integers. These are the orbits starting from the integer 199 and the adjacent odd integer 201. And I've recentered the axis so that the termination at 1 is always at the right hand extreme. So if you do 201. It terminates after 1, 2, 3, after basically 4 iterations. And once you're at 1, 1 is a fixed point. Okay, so you can easily show. This conjecture is beautiful as a way of engaging people with pure mathematics, because actually there are various things you can state and prove fairly easily, but they don't get you all the way to the proof of the whole thing. For example, you can show that 1 is the only fixed point very easily. But if you start at 199, so this is kind of sensitive dependence on initial conditions. Start at 199, it kind of oscillates around for a while, and it looks like it's going to go through exponential growth, then it crashes down, then it really takes off. So you get extreme events. It goes up to 3,000, but then it hits something a little over 3,000, and it gets sucked right down to 0 again. And this really it involves a dynamical system flavor, because essentially you can the question of whether it terminates as one is whether on average the iteration is a contracting map on the integers. Because if you multiply by 3, you expand by a factor of 3. If you divide by 2 just once, then you're still expanding by a factor of 1.5, so you can run off to infinity. But sometimes you divide by 4 or 8 or even higher numbers. And so whenever you hit 4 or more division by 4 or more, you're contracting. So it's a play against the expansion by 1.5 versus the contraction that on the average will answer the question of whether it all contracts down ultimately in the long-term average and gets to 1. And I suspect that when an answer comes to this conjecture, it will come through some kind of dynamical systems. But discrete dynamical systems are very challenging, because you don't have the continuity relationships to work with that geometrically constrains so much of the rest of dynamical systems. Orbits can hop right past each other. And now, thinking of simple dynamical systems, I just want to mention something I'm sure most of you have seen, which is the simplest continuous dynamical system. Dynamical system on a continuous entity, which is the dynamical system of iterated maps on the real line. You take a real number x, and then you subject it to a function f of x, and then you iterate and you ask what the orbits are. And so the discrete logistic map, which is just the discretized version of the logistic equation, it just says you take x, you multiply it by a real number a, which is positive, and then you multiply it by 1 minus x. And so this has two fixed points, an unstable fixed point at x equals 0, and a fixed point at x equals 1, which may or may not be unstable depending on the value of a. And I first think this simple chaotic system, that was really my introduction to chaos. And I first encountered this map at a Harvard physics colloquium. I was a Harvard physics undergrad. And although everybody was obsessed with particle physics in the Harvard physics department, especially quantum field theory, there was a little emerging interest in what's now called soft matter physics, very small. You got very little of it in a physics degree at that time. But the colloquium committee had invited Robert May, who was at Princeton at the time, to give a talk about the logistic map. Robert May was applying it to cicadas, to cicada population booms and busts. And so the idea that you got such amazing structure out of such a simple map, and many of the beautiful theorems that we now know in association with this kind of thing were not known yet, like the period doubling bifurcations and the Feigenbaum universality theorem and so forth. But just as an example of the way this illustrates the chaotic behavior and the way chaos comes in. This is as a function of the bifurcation parameter A. This just plots the positions of all the periodic orbits. And some of these are unstable periodic orbits. And so there you have your fixed point at 0. Here you have another period 2 orbit, and then you get a pair of periodic orbits branching off of that, and then more and more. And if you zoom in on all of the stuff here, you find that in fact, as you approach 4, you get a dense set of unstable periodic orbits, which, as we now know, are the basic organizing structures of chaotic systems. In some sense, chaotic systems are always near an unstable periodic orbit, and the probability distribution on strange attractors is determined by how long you stay near each unstable periodic orbit. And this idea is actually just starting to be employed to understand partial differential equations. Finding unstable periodic orbits for PDEs is really challenging, but methods are evolving that enable that to be done. And I think they'll be very promising. They are already showing up as very promising in understanding coherent structures, repetitive structures in nonlinear systems pertinent to the atmosphere. Okay, now fluid dynamics, although I spent my undergraduate degree in physics, and everybody was rushing to get to quantum field theory in those days, certainly at Harvard, and I think at most physics departments, fluid dynamics was always my first love, together with number theory, at least once I got to where I could understand partial differential equations. And I used to save my pocket money in high school and buy Dover reprints of classic fluid dynamics books, that and science fiction. It was almost the only thing I read for a lot of years when I was in my teens. But fluid dynamics is a bit like Go. You have really a set of equations, say, for incompressible fluid dynamics that really just embody Newton's law. And out of that, you get all sorts of structures. You get vorticity, you get instabilities, you get jet structures. This is one of Leonardo da Vinci's chalk drawings of vortices. You get the formation of the vortices, you get turbulent transport, you get coherent eddies, all sorts of wonderful things. Out of a set of equations that is fundamentally unstructured, you get all sorts of emergent phenomena, which is really wonderful. And I didn't really, so as I said, as a physics undergraduate in those days, in the US, you just didn't see much fluid dynamics. But I had a fellowship grant after my undergraduate degree that took me to Cambridge for a year, except the dollar was strong at the time, so it actually lasted a year and a half before it ran out. And I felt like I had died and gone to fluid dynamics heaven. That's where I started working on hydrodynamic stability theory. And Nigel Weiss, who passed on recently, he was my advisor in the Department of Applied Mathematics and Theoretical Physics. And my first encounter with geophysical fluid dynamics was through Mike McIntyre, whose lectures were a real inspiration. And then I came back and I went to finished I did my PhD at MIT, starting with stability theory for instability of coherent vortices. And Sheila Widnall was my thesis advisor in Aero and Astro. I more or less went to Aero and Astro because I really wanted to work with Sheila, who was doing really outstanding work on instability of coherent structures. And Morten Landahl was in the department at the time doing really good work on instability and turbulence. Sheila eventually became Secretary of the Air Force, which was interesting because she actually didn't have at the time a whole lot of interest in wing theory. She was a theoretical fluid dynamicist like I was at the time. But I took by happenstance, I took one course in the meteorology department from Jewel Charney, who later became a member of my thesis committee. And Sheila and Jewel got together, and Jewel had the faith in me that with one class in dynamic meteorology, maybe I could get interested in being a meteorologist. And they offered and arranged for me to get an assistant professorship in the MIT meteorology department. It had not yet merged. I'm not sure that sort of thing would happen these days, but it was transformative. This is where I started work on coherent structures and their instabilities. That work I published while I was still at MIT. Jewel Charney got me involved with the Alpine experiment, flying around looking at gravity waves. And that started many years of work on stratified flow over mountains. Through the teaching that I did in my first courses at MIT, I learned about baroclinic instability, which launched a lot of work on the subject of things like local and global instability, most of which I taught myself through teaching the stability theory course that I put together in my first year at MIT. And I worked on multiple equilibria and weather regimes. I want to actually mention that where does global warming come in? So during the year, I joined the MIT meteorology department in 1980, and that's actually when the Charney report, the first assessment of carbon dioxide and climate, came out. And I remember Jewel in the lounge, in the faculty lounge at MIT, people were quizzing him, including Dick Lindzen. This business of global warming, do you think it's something real? And Joel was saying, yes, it's real. We will probably double carbon dioxide, and it will be the biggest change on Earth since the last ice age. And it was prescient. And you can see this is the small list of people that were involved in doing the assessment of the calculations that had been done at the time. Most of the conclusions of the report have turned out to be correct. This was the last moment where it could be said that the science was not well enough understood to justify action, and it's really tragic that it's taken so long for the world to finally start the beginnings of taking action on decarbonization. But I often think back and ask myself, why didn't I drop everything and start working on global warming at the time? But it was not something that was actually much in discussion in the MIT meteorology department, or indeed anywhere in the United States, despite Joel Charney being at the MIT meteorology department and having led this landmark assessment. We were all taken with multiple equilibria in the Charney-Devore model and various kinds of nonlinear resonance, detuning, and things like that. It was a world of GFD, and the GFD people did not interact all that much with even radiative transfer or thermodynamics people at the time. And that shows in how long it took me to actually make a transition away and finally get to working on where I could actually be on the IPCC report and make a material contribution. Now I'm going to quickly skip over my years at GFDL and Princeton, except I want to say how much I learned from Isaac Held. I never did a PhD in geophysical fluid dynamics or atmospheric science, and working with Isaac and hanging around Isaac was like the PhD I never had. And I want to get on to the other kinds of physics I've worked on, but although in some ways, these were some of my most productive years in geophysical fluid dynamics. I don't want to go into what I worked on at that time because I'm running short on time and I want to get to some of the other things. But it was truly an educational period in my career. Okay, now towards the end of the time and getting back to simple ideas and finally getting back to nonlinearity, towards the end of my time at Princeton, I started reading the book by Guckenheimer and Holmes on nonlinear oscillations of dynamical systems. And ideas were beginning to emerge about applications of these things to fluid mixing, area preserving maps to fluid mixing. So why not do it to GFD? So that's what I started working on. And so then I finally got back to dynamical systems and nonlinearity. And the idea behind chaotic advection and a whole raft of things that follow is one of these simple ideas with enormous consequences. We just take a time-dependent velocity field in 2D or 3D and you form the trajectory problem. Because the velocity field is a nonlinear function of position, you get a nonlinear ODE for R, and if it's time-dependent 2D or even steady 3D, that's enough to support chaotic trajectories. And indeed, generically, some of the trajectories are chaotic. And this induces an area or volume preserving map on the plane. There's, I'll skip this first, but there's a Lyapunov exponent, which turns out to be a key characterization of the kind of mixing. And associated with the velocity field V is an advection diffusion problem, which is a linear problem for the concentration C. But underpinning it is a hyperbolic nonlinear problem, hyperbolic in the sense of PDEs, for the trajectories, which has an enormous organizing influence on the kinds of structures that you get in the course of mixing, in particular exponential amplification of gradients and the formation of filamentary structures. And it's just one example of how generic these things are. This is the unstable manifold for the advection problem for a superposition of two Rossby waves, two linear Rossby waves. But then if you look at the vorticity in a fully nonlinear 2D beta channel simulation, this is the time sequence, you can clearly see the signature of the unstable manifold in the vorticity itself, even though this is a fully nonlinear simulation. There was a whole raft of further work that emerged from this, including a work on Lagrangian coherent structures. That's the name that George Haller gave to that subject in the end. And then ultimately, when I started to learn about water vapor, if you just add condensation to this simple advection model, you get a whole raft of new phenomena, which I called the advection condensation model behavior. Stochastic drawing gives you a theory of relative humidity dynamics and so forth. We're applying some of these ideas to the chemical reactions in exoplanets where the main mixing is not due to convection, but due to large-scale wavy type flows. Okay, so at the beginning in Chicago, when I moved to Chicago, which was a transformative period in my career, I was still concentrated on GFD, but it was a small, diverse department, and we all had to do a little bit of everything. My colleagues, this was a geology department that was mixed with an atmospheric science department. My colleagues were getting me interested in things like ice ages and Cretaceous warmth, which required more physics than just the dry quasi-geostrophic GFD that I've been working on for so many years. And also at some point, I started teaching radiative transfer and energy balance, which is how I started to learn that stuff. And then what really happened that catapulted me into thinking about water vapor and tropical dynamics is that a paper by Ramanathan and Collins. Ram had been at Chicago briefly before he moved to the West Coast, and called the thermostat hypothesis, which reported to show, based on data, that shading by high convective clouds would keep tropical temperature from ever rising above 302 Kelvin. And I was teaching this in my tropical climate class. And I got more and more confused about how to explain what they had actually done. Matt Huber, who's now on the faculty of Purdue and quite distinguished in climate research and paleoclimate research. Matt Huber was an undergraduate in the class at the time, just declared, hey, it actually doesn't make sense. And I realized, yeah, it does not make sense. And so I needed a model. I needed to quantify why it didn't make sense in terms of a simple model. it wouldn't be just mired in a bunch of GCM calculations. And so that gave rise to this paper, Thermostats, Radiator Fins, and the Local Runaway Greenhouse. I really had to delve into doing all sorts of things I had never done before. But so the model that I came up with, which came down to a few simple equations, involved a box I called the furnace, and then the radiator fin, where you have ascending motion here and you have moist convection. Then you have subsidence in a dry, fairly cloud-free atmosphere. Here, less water vapor, therefore more radiation to space. And the principle used to couple these two together was the principle that in the tropics, where the radius of deformation is large, the temperature in these two boxes should be approximately the same. And that constraint actually allows you to diagnostically determine the ascent and descent and the mass flow between the two boxes. So this is now called the WTG approximation, after it was vastly elaborated and improved by Adam Sobel and others. But the idea goes back to Jewel Charney's early work on tropical dynamics, although it was never codified in a simple climate model like this. So in order to shoot down the thermostat hypothesis, I wrote down a short version of this, which was immediately rejected by Nature. And then I elaborated the model, and it got way beyond just the function of shooting down the thermostat hypothesis. I submitted it in December 1993, and it took a whole year for it to get accepted. That first acceptance of a paper with water vapor in it was 15 years after my PhD, which shows how long it took me to get involved in radiative transfer and water vapor. And it was also my first use of the runaway greenhouse concept, which I had learned about from a paper by Nakajima that et al. That I handled as an editor for Journal of Atmospheric Sciences. So the aftermath of this scientifically was somewhat nasty, in that I actually got, because of my dissension from the thermostat hypothesis, I actually got ejected from the NSF Cloud Chemistry and Climate Center, which was kind of built around testing the thermostat hypothesis. But after 5 to 10 years, most of the community realized I was right. But it was such an obvious and glaring error in the thermostat hypothesis. It doesn't actually need this 25-page paper to shoot down it. It just takes 3 or 4 pages of this to just point out that the top of atmosphere energy budget is what really controls the surface temperature. And since the clouds almost cancel out from the top of atmosphere, they don't actually have a shading effect. And then there was also a fundamental error in the thermostat, in Rahm's thermostat paper, on what controls the trigger temperature for deep convection. Okay, so a lot of water vapor papers follow. Yeah, we're running, and they need to wrap up pretty soon. So I won't go through any of the detail, but this paper was a kick in the pants that launched me into suddenly knowing how to work with these other kinds of climate physics, and they each had their versions of simplifications that made it possible to make progress in terms of simplified models. And I won't go through the details of that, but the paper is what launched me. The hunger to tell people how the tropics really worked and how there wasn't a thermostat there was what actually fired me up to actually leave my dry GFD world and get involved in this much more rich set of physics. And the other thing that happened while I was at Chicago is that I started teaching a global warming course for non-specialists, Phi-Sci 134. I taught that with David Archer, and he learned radiative transfer from me, and I learned geochemistry from him. And what I learned about geochemistry in those years has played very much into subsequent work that I've done. Now, I want to mention one of these things just as an example of how teaching can turn into science. My first paper that used radiative transfer for planetary dynamics was this paper in Science, which was an idea about warming early Mars. That is, early Mars was warm and wet at a time when the sun was faint. So how did that actually happen? And ordinary carbon dioxide gaseous greenhouse effect doesn't do it. But you do form carbon dioxide clouds in those thick CO2 atmospheres. And so when I was on sabbatical in France, I met up with Francois Forget, who is a grad student at the time, just finishing his thesis. We met in the coffee room, which was also where the Xerox, the printer stuff came out. And we teamed up together and we turned this vague idea into a paper that was quantified. And we thought we had the whole answer to warm early Mars. It turned out to be only a part of the answer, but it's still a phenomenon, scattering greenhouse effect, that is of universal importance. And just to give you an idea of where the idea came from, you've all seen these erroneous pictures of the greenhouse effect, which show infrared being reflected by the atmosphere, whereas in fact, in the Earth's greenhouse effect, it's a matter of absorption and re-emission. But I often included the problem in my climate class. Well, what would happen if you did have some substance in the atmosphere that reflected infrared rather than absorbing and re-emitting it? And at a random IUGG session, I learned that CO2 ice clouds actually do mainly reflect infrared. And I put this together into a really clever argument, which I sent to Nature, and was almost immediately rejected by Nature. We didn't convince anybody until we abandoned this clever argument and just developed a radiative transfer code that would handle the scattering greenhouse effect, which was not at all common at the time, and actually did the calculation. And later, I've used this clever idea to explain what was really going on. It eventually appeared in Journal of Atmospheric Sciences. But I learned a huge amount about Mars from Francois, who was only a graduate student at the time. Okay, now I'm running short on time, and I want to just spend a few minutes on exoplanets. I'll just mention my debt to Paul Hoffman and Dan Schrag, who introduced me to the snowball Earth problem, which I wrote many papers on. And that brought in yet more emergent phenomena, like the interaction between thick sea ice, sea glaciers, and dust, and the albedo feedback. And then I started working with Jonathan Mitchell, who was a graduate student at the time, and between the two of us, we got interested in Titan, which has a methane-based hydrological cycle, which turns out to be rather like a warm Earth. So finally, exoplanets. This is my last group of slides. When exoplanets were discovered, then it was like a gift from the gods. I never expected to see this happen within my career. But suddenly, astronomers were able to detect exoplanets and now even detect what's in their atmosphere. And it just unleashes a whole wonderful playground, which I jumped on new climate effects that use the same physics in different combinations, like the effect of the stellar spectrum, especially the planets around red dwarf stars, which put out much more of their output in infrared. We have hydrogen-dominated warm small planets. And that introduces new moist convection phenomena and new large-scale dynamics, because H2O, water vapor with a molecular weight of 18, is much heavier for the same pressure and temperature than hydrogen. So it suppresses convection and gives you very strong virtual compositional buoyancy effects, which affect baroclinic instability. And there's even a planet out there, which is one of these gassy hydrogen-dominated worlds with water, K2-18b. We have rock vapor clouds on hot planets, lava planets with a permanent dayside magma ocean that outgasses silicate metal atmospheres that go transonic and snow out on the night side, and much, much more. Just as an example of how old ideas come back in, this is a simulation of Trappist 1D. This is a tide lock planet, which has a permanent day side and a permanent night side. This is where the sun is beating down, and it's a slow rotator. It's in something like a 10 Earth day orbit. So the whole planet is in the weak temperature gradient regime, and you can see up here that the temperature is virtually independent of position from the day side to the night side. Whereas when you go near the ground, you can have shallow layers where you can have a substantial temperature gradient. So you can still have the situation where it's sub-freezing and frozen on the night side for an ocean world, but have open water on the day side. So this was just the weak temperature gradient approximation, which I've turned into a series of models of exoplanets coming back in a completely new context. Other GFD ideas that come back in a new context are the Matsuno-Gill model of waves in the Earth's tropic, which is the basic idea of our understanding of the Walker circulation and of tropical waves. And this is a simulation of a tide-locked, the 500 millibar height and the height in color and wind pattern on a tide-locked exoplanet. This is the substellar point there where you have high pressure. You get these Rossby vortices, which are Rossby waves, and then you get a Kelvin wave down on this side. And you get a Walker type circulation, except it's global. There are interesting differences because you actually get a strong jet on such planets in the tropics, which you don't have on Earth, and that affects the wave dynamics. And so I think, I think I will just call it. I will just show you one animation to wind up, just to point out that it's still. This will be just my. I'll just get my animation up, just to show you there's actually still a lot of dynamics to know. Although learning all this other physics is important, dynamics is still extremely important. And I sometimes think people are using GCMs too much as a crutch and are not getting the kind of training and fundamentals of GFD that people used to back when they didn't need to know as many other different things to do research. So this is the temperature pattern on the planet 55 Cancri E from a simulation. And you see, you do get these Rossby vortices, cold Rossby vortices there. You get something like a Kelvin wave, but the hot spot is by no means stationary. We've got all these eddies being flung out. And we don't understand the dynamics of these things very, very much. And so that is very well. And so that is a frontier area. And then if you combine that dynamics with things like the question of where do you form clouds and where don't you form clouds, you have an unlimited scope of new things to think about. So, my concluding remark, I won't put up the slide. The concluding remark here is that a certain amount of randomness in your career can be a good thing. It's like simulated annealing. It keeps you from getting stuck in just one rut and boots you into thinking along new channels. And this other subtext is that although there's a vast amount to be done by putting together various kinds of physics like water vapor, condensation, radiant transfer, chemistry, geochemistry, and so forth, it's still important to know GFD. And so I would make a plea for sound grounding in GFD to remain part of any curriculum in atmospheric physics. So thanks a lot. Okay, and thank you for indulging me running over a little bit.
Thank you very much for this very interesting presentation. It's very interesting to see that teaching can become science. I have to teach a new course soon, so I'm very happy to. I hope I will manage to do the same thing, but probably this looks very ambitious. So,
well, actually, and that was another one of my take home points is that teaching is really essential. It's only teaching and contact with people who are newly learning the subject that keeps you confronting the fundamentals. And often the things we think we understand, we don't understand as well as the field thinks they understand them. And so it's that contact with undergraduates and graduate students that I think is really essential to any productive research life.
That's great. Maybe I can ask a first question. Are you in contact with any sci-fi authors for all your planetary climates?
Oh, yeah, I have. I actually, I'm not in very close contact with any science fiction authors, but I have done things like written to the author of the Lady Astronaut series, Koval, Robinette Koval, about a particular scenario for the Earth going into a runaway greenhouse, which doesn't quite work, although the books are really very well plotted. And so I've had some contact with that. I had some contact with Ben Bova about a similar plot line, but not very active. I don't go to sci-fi conventions and things like that. But
there's I see a lot of potential there.
Yeah. Oh, there is actually. It took a while. Actually, I use a lot of science fiction scenarios to make up problems for my class and in my book. But it took a while for the science fiction community to really start exploiting the possibilities of exoplanets. And the first few books about tide-locked exoplanets actually got a lot of things wrong, but now they're starting to get it right.
Okay, I'll start answering the questions by the audience. So Diego Jimenez de la Cuesta Otero is asking, don't you think that in principle you can take only part of the chemistry complexity that is relevant to the problem, just as one would only take into account weathering when this process becomes relevant for the time scale?
Well, I mean, I would like to think that, and to some extent, in a few cases, you can extract subsystems that give you insight as to the basics of what's going on. Although often finding those subsystems requires a lot of poring through the massive chemical networks. But as an example of things where sub-networks do give you some insight, there's the Chapman reactions for ozone in the atmosphere. And then there's also McElroy's set of reactions for turning carbon monoxide back into CO2 in a Mars-like atmosphere. And to some extent, the simplified reaction networks we're using to look at steam atmospheres and regeneration of water from photolysed water that makes hydrogen, they're a little bit like that. But still, the progress in chemistry has often involved a lot of comprehensive understanding of the complex system before someone has the insight to like Crutzen and others did about the ozone destruction by CFCs, to know what was the critical thing, what was the critical step. We don't have a very organized way of doing that. Although one of my postdocs now in his thesis developed a critical path method for taking a complex reaction network and then finding out what are the rate controlling steps. And this is actually a promising way, I think, for maybe boiling down some understanding from complex reaction networks. But I still find atmospheric chemistry very intimidating.
So the next question by Stefan van Itzen. Thanks for this very nice presentation. Concerning your last remark on the random trajectory through science, do you think that in the current period, such type of trajectory is still possible for young scientists when they are under pressure in publishing a lot?
Oh, that's an excellent question. It's actually one of my worries. It's one of my worries that some of the assessments, bibliometrics and so forth, would make it hard to do things the way I did. And and something that I didn't make explicit is that I had the equivalent of tenure at a very early stage in my career, which protected me to a considerable extent. I think people are unfortunately spending more time I never had a postdoc, and people are spending more time at postdocs and getting on the tenure track later, which cuts into your time for sort of freewheeling development of new ideas. And I'm worried about that. And I would like to think that the way I did things was still possible. But my tenure protection was really essential to my ability to fight this somewhat unpleasant thermostat fight, which all turned out, we're all in speaking terms again. But if I had been some assistant professor worried about getting tenure at the time, I would have been really intimidated about taking on something like that. So I do worry. Yeah, I do worry about career trajectories. The answer is that there should be about 5 times as many academic jobs as there are, because all of this competitiveness comes from there being, too few academic jobs relative to the amount of talent that's out there. And I'm just awestruck by the amount of talent that's out there. And I wonder, how I would have competed with some of the CVs that I see when I advertise for a postdoc. So there's huge talent out there, and I think maybe more talent than ever. But to some extent, people are not having the sort of the freedom to exercise their creativity because of these various pressures. I don't really know what the answer is, because nobody's going to create 5 times as many academic jobs. But.
Unfortunately.
Yeah.
The next question by Stefan Bühler is radiation more go or more pachinko? The spectrum is very complex, but the cooling rate is pretty constant throughout the troposphere.
Well, so I think radiation is more go than pachinko. Although you can find pachinko-like elements in radiative transfer theory, like the zoo of different spectral characteristics, the zoo of different lines that something like water has, which actually do affect what's going on. But I think it's more like go in the sense that the Schwarzschild equations are one simple linear ordinary differential equation written many times over. And then there's some technical aspects for how you actually deal with the fine scale spectral dependence of absorption characteristics. But the underlying physics is more go than pachinko. The other reason I think it's more go than pachinko is that actually, if you have a really thorough understanding of gray gas behavior, which is just the one equation, that carries you pretty far. Often in radiative transfer books, people were not getting a full understanding of gray gas behavior, which is why I devoted so much to developing mathematics of gray gas behavior in my planetary climate book. But it's an interesting question, because there are some aspects of radiative transfer that are more pachinko than go when you get down to the details of individual gases, and in particular, the strange approximation correlated K that we use to deal with them.
I guess it's a bit like go. It's computationally very intensive.
Oh yes, it can. Yeah. So simplicity does not necessarily mean easy to compute. So there's conceptual simplicity, but which can require a whole lot of computation.
And then I accidentally skipped the question of Rodrigo Caballero. Hi, Ray.
Oh, Rodrigo. Hi, Rodrigo. Yeah, Rodrigo, you were in the talk, although I was rushing through it. So your name was in there because, yeah, especially in the work we did on Titan and on and on Klimt, Rodrigo was the original author of the Python climate package Klimt, which is still alive today, and we use it a lot at Oxford. But go ahead, Rodrigo. Yeah. Yeah.
So he says, thanks for a great talk. Could you say something about how things learned in exoplanets could come back to illuminate Earthbound problems?
Yeah, I mean, sometimes in grant proposals, you see, exoplanet studies, justified as a way of illuminating things going on Earth. I don't like to use that justification myself all that much because although I think it can happen, it's not the main reason we do the exoplanets. We do it because it's just mind-blowingly interesting and addresses questions like, are we alone in the universe? But I think the advantage of that sort of thing, the advantage of working on really out-of-the-box problems, that first of all, it challenges your model. So sometimes if you just run your model and your climate models, whether conceptual or GCMs, in cases that are pretty close to the current Earth-like climate, you miss bugs or problems in formulation that become blindingly apparent if you push them outside the box. Sometimes in planetary sciences, in the solar system, it's alerted people to the importance of things like dust or aerosols that weren't being thought of in connection with the Earth. A lot of the original work on sulfate aerosols was originally done for Venus. And so I have no doubt that some of the things that we do for exoplanets will trigger thinking outside of the box, which will cause somebody to say, well, hey, maybe this could happen. This could happen on Earth too. But that's a kind of an unpredictable thing. And I think if I look at what I consider to be the biggest problems with understanding Earth climate, which are low clouds and low cloud behavior, working on exoplanets is not necessarily the way I would most going about addressing that kind of problem. But it's good. But the other thing about exoplanets, though, is that it's incredibly attractive to people newly entering the field. It's a wonderful magnet to attract people into atmospheric physics because it's just so fascinating. And so many people that get attracted in from exoplanets, people who might otherwise go off to become bankers or something, they get interested in the atmosphere, and some of those will actually work on Earth climates too. And their training and thinking about fundamentals from thinking about exoplanets will serve them in good stead in thinking about Earth climates. That's where I sort of feel like it fits into the picture.
Thank you. A question by Andrei Spiridonov. How similar to the modern Earth was early Venus, climatically speaking, and are there any good evidence or theory on this question?
Oh, it's a wonderful, wonderful question. There's a lot of work on Venus. Quite a lot of work on exoplanets actually has come back to influence our thinking about solar system planets, notably Venus and Mars. One of the puzzles about Venus is whether it ever had liquid water at the surface. And there's been a lot of interesting theoretical modeling. In one model, Venus started hot, lost all of its water before it ever got cold enough to condense out into an ocean at the surface. And actually, whether or not it cools down fast enough to make a liquid ocean in the early days when the sun was fainter depends a lot on cloud behavior. So actually, we're gearing up in my group to do GCM simulations of hot runaway atmospheres with clouds in to try to address this very problem. So like every problem in climate, clouds come back to haunt you at some point. First of all, it's not necessarily true that Venus ever had a liquid water ocean. It's also possible that Venus was born dry, that it never actually got a supply of water to begin with. But if Venus did have a liquid water ocean, there are questions about whether clouds could have protected it up to fairly recent times. Work at guess by Mike Way suggests that an ocean could have persisted, up until 1 billion years ago or something like that, if clouds had prevented a runaway greenhouse. But most people seem to think that that's an unlikely scenario. That Venus, if it did have a liquid water ocean, lost it, several billion years ago through leakage of water to space from the planet being very hot. The problem is that the whole Venus crust is young. Unlike Mars, there's no geological record on Venus that goes back more than, I don't know, 500 million years. So even if we did a sample return from Venus or an in situ measurement of what's in the surface, there's not likely to be any geochemical record of whether Mars had a liquid water surface. We get some indications from isotopes in the atmosphere that Mars did lose water, but they don't really constrain how much water and whether Mars lost water in an entirely vapor phase or whether it had a liquid ocean. The isotopes don't discriminate that. So I don't know how we'll ever actually answer the question of what really happened on Venus. We might answer that question by looking at Venus-like worlds that haven't lost all their water yet among exoplanets. So the field of comparative planetology could tell us quite a lot. But as far as the modeling, as far as the theoretical and modeling work goes, this is an extremely active frontier area. What is the full history of Venus? And it actually ties in with the question of whether there could be life in Venus clouds, because Venus would have had to evolve from a situation where it had a liquid ocean and life emerged. And then as the planet lost its water and the water retreated to just this little cloud layer and the planet got hotter and hotter, was there a continuously habitable layer that bacteria could have lived in all of this time, which is something I sometimes think of working on, but it hasn't floated up to near the top yet.
Yeah, so that's nice to think of exoplanets as a kind of looking into the past of our planets or into the future. So that's another question by Diego Jimenez de la Cuesta. Okay, sorry, Otero. Just as you consider important to have a solid GFD knowledge, then a solid knowledge in dynamical systems should be as important, isn't it?
Yeah, well, so this is a problem I always wrestle with is how do you actually arrange graduate training now and postdoc training so that people can work on real frontier problems? Because it really is true. It really is true that to work on the frontier problems now, you do need to know more different kinds of physics than people needed to work on what were considered frontier problems when I was a graduate student. And so how do you actually do that without getting too shallow? And so I think the answer is partly to pick, say, 2 or 3 areas to know reasonably well, one of them to be an expert on, but also to learn how to talk to other people who you can collaborate with. And then by collaborating with them, you start to learn it. But I think ultimately, it's a lifelong learning process, and you have to start somewhere, but then hopefully have enough background that you can grow out from there. And I do think that everybody should know a certain amount of dynamical systems, because it's one of the great tools of mathematics that allows us to analyze a simple model. What's the point of having a simple model if you just simulate it and don't have a framework for understanding it? And dynamical systems give us that framework. And I think, certainly everybody should see the logistic equation and know about Lyapunov exponents and Lorentz system and things like that. And I think they should know something about area preserving maps and Hamiltonian chaos. And as it happens, another book I'm working on writing, although it's 10 years overdue, is a book using Python for exploration of fundamental mathematics, and included quite a lot of dynamical systems problems in it, which I hope will make it easier for people to get an introduction to this subject in a way that blends computation and theoretical work. But so some people will go far with dynamical systems. Other people will decide to spend more time on knowing radiative transfer. But I'm just saying the thing that always seems to fall by the board these days is GFD. And the number of people who really thoroughly understand, say, the Charney problem for baroclinic instability, the Charney-Drazen theorem, stuff like that. It's not a foregone conclusion that people coming out of graduate school know these things. Now, some places they do, but it often just falls between the cracks. Pseudo-momentum conservation, things like that. And so I'm just making a plea that we don't forget about it. I'm not actually saying it's the prime thing, but I still think it's an essential part of understanding how atmospheres operate.
Another question by Gavin Schmidt. He wonders if in situ Venus drilling is possible with regards to the previous question.
Oh yeah, you could drill. Operating anything on the surface of Venus is a challenge. You don't have much sunlight to provide solar power, but we already use thermal. That's with an L, thermal nuclear power on Mars, and for outer planet missions. And so you could send a nuclear powered surface device and maybe drill in. But the thing is, if the crust is fairly young, you could drill down a half a kilometer, which would be actually a stretch for extraterrestrial stuff. You could drill down a half a kilometer and you still be getting sort of young basalt. It would still be transformative to even understand things like sulfur cycle and maybe even date the crust, because it's hard to date the crust by crater counting because you don't get many craters on Venus. We don't know what a weathered crater looks like on Venus. And so there would be transformative things you could do if you got even a couple meters into the crust or just scraped the surface. Working at those temperatures is a big challenge, and nobody is really proposing new landers in the foreseeable future. And sample return mission is not likely because of the gravity well. But I don't think any of these things would actually tell us much about whether Venus had an ocean, because it's almost certain that the evidence for whatever primordial ocean there might have been has been wiped out.
Okay. Question by Valerio Lembo. Shall we include the moist runaway effect as an anthropogenic climate change scenario compared to current emission paths?
Yeah, I think there have been, actually, in some ways, Jim Hansen started off the argument about, could the Earth go into a runaway? And actually, there's also a lot of loose use of the term runaway climate change, and this and that, which is not referring to the kind of runaway water vapor greenhouse that Venus had. But at one point, Jim Hansen seemed to be saying that if we burned all the coal and oil, Earth could go into a runaway like Venus. And I think that's extremely implausible. Actually, there have been estimates from radiative transfer, radiative convective models, as to whether this could happen, and it's extremely unlikely. And the basic reason it's unlikely is that the reason it's unlikely to trigger a runaway greenhouse through increasing CO2 is that you need a certain amount of absorbed solar radiation. You need a threshold of absorbed solar radiation that you have to exceed before you can actually sustain a runaway greenhouse. And so if the Earth is just not getting that much radiation, CO2 will make it warmer, but it can't actually trigger a runaway. Now, there are some exotic, metastable conditions where you could imagine that we're in a metastable non-runaway state, and increasing CO2 could kick us into a runaway state. I think most estimates are that we're not in one of those situations. But the uncomfortable thing is that what prevents us from having a runaway are two things: reflection by clouds, especially low clouds, and the fact that most of the atmosphere is subsaturated. If you took away all the clouds, and if you saturated the atmosphere, which I don't think is actually possible, but if you took away all the clouds and you saturated the atmosphere, the Earth would go into a runaway. And it's actually, given the uncertainties about cloud effects, it's hard to 100% say that this couldn't happen. But I think paleoclimate gives us strong evidence that it's not at all likely, because if the Earth was going to go into a runaway, it probably would have done that during the Paleocene Eocene thermal maximum, when you had a big pulse of CO2 and the sun was almost as bright as it is now. And I think that that gives us some confidence that our models that say you wouldn't go into a runaway from a pulse of CO2, that they're probably correct. And I thought it was problematic for some people to be making a noise about the Earth going into a runaway greenhouse and turning into Venus, because then if you publish a blog piece, which I did, that says why this is extremely unlikely, well, this is an incorrect statement, then people say, oh, we ducked a bullet, global warming isn't so bad, we're not going to turn into Venus after all. But that doesn't mean it's not so bad, because a 20-degree increase in temperature would not turn us into a runaway, but it would still be lethal for a lot of surface life on the Earth, especially mammals.
So there's a small follow-up question by Valerio. He asks, excluding rate-induced transitions?
Oh, actually, rate-induced. So actually, this is an interesting kind of bifurcation theory. That a lot of bifurcation theory, like the example I showed of the logistic map, involves essentially what might be called adiabatic changes in your control parameter. You go through a series of quasi-statistical steady states, but there are cases where you can make a transition from one branch of the solution to another by a rapid increase in the sufficiently rapid increase in one of your control parameters. And CO2 is like quintessential control parameter of our own climate. There's no plausible case that a rapid increase in carbon dioxide would trigger a runaway greenhouse. You need to come up with a scenario where a rapid increase could saturate the atmosphere and make the low clouds go away. Now, there's a lot we don't understand. So as I say, I can't 100% rule that out. And it is true that the difference between the Paleocene Eocene thermal maximum and what we're doing now is that we are potentially increasing CO2 by possibly a factor of 4 or more over a time span of 200 years. In the PETM, nature probably took at least 10,000 years to do that, maybe more. So this is unprecedented, especially if we do burn all the coal that's out there and heaven forbid, find more fossil fuel resources and seafloor clathrates or something like that. Now, we could basically make the Earth uninhabitable, even without going into a runaway greenhouse. I think rate-induced transitions could play a big role in things like deglaciation of Antarctica and a lot of vegetation feedback, so, say die off of the Amazon rainforest, things like that, especially when there's biology involved. I don't actually see a very clear scenario where rate-induced transitions could lead to a runaway greenhouse. But it hasn't been explored. It hasn't been explored. But since it definitely involves clouds, I think it is the sort of thing that has to involve enough dynamics to do a reasonable job of what the clouds are doing.
Okay, I'll just take the final question by Sergio Rubin. With the current knowledge of the Earth and exoplanets, can we make Mars habitable? And if yes, how? If not, why not?
Yeah. Well, so I mean, we don't even need to go to exoplanets to figure out how to make Mars habitable. It's a matter of the technology that would be needed to warm up Mars. And so right now, the sun has gotten bright enough that if you gave Mars a carbon dioxide nitrogen atmosphere, then actually you could warm up Mars sufficiently to have liquid water at the surface. And there's plenty of liquid water tied up in the permafrost and the ice caps. But you need something like maybe a bar of nitrogen and 2 bars of carbon dioxide. And there's a problem that carbon dioxide is actually toxic from acidosis at those levels. So it wouldn't be a breathable atmosphere if you used carbon dioxide as your greenhouse gas. So maybe, so there have been papers written on this. Yuck Young wrote one. So maybe instead of using carbon dioxide as your greenhouse gas, you want to use something like sulfur hexafluoride or perfluorocarbons that are good, can be good greenhouse gases in lower concentrations and are not toxic in the concentrations needed to warm Mars. And actually, after I wrote after Francois and I wrote the Mars cloud paper, I was getting a lot of emails from Mars terraforming people who wanted to use specially designed reflective clouds to warm up Mars. But you also need some surface pressure. So you need a bar of something or other just to keep from things boiling away, or maybe a half a bar. And that's a lot of mass under Martian. That's a lot of mass under Martian gravity to move over there. And until we develop the technology to take comets and collide them with Mars to just provide some volatiles to it, we can't do it. Now, my former postdoc, Robin Wordsworth, who I might have mentioned briefly, but I was running past, Robin was a fantastic postdoc, and we just did a huge amount of work together on exoplanets when I was just getting into exoplanets. So Robin's at Harvard now, and he came up with this really fascinating idea to at least make agriculture possible on Mars without actually giving it a breathable atmosphere. So you get a solid greenhouse effect from silica aerogel, really light stuff, which lets light through, but is an incredibly good insulator, has incredibly low thermal conductivity. And so if you just covered large parts of the surface of Mars with silica aerogel, you would actually easily warm up the regolith on Mars to the point where you could grow crops in it. And this is a solid greenhouse effect is a concept that came from study of icy moons like Triton and so forth, or even it plays into deglaciation of snowball Earth and various ways of melting clear ice. So terraforming Mars with a breathable atmosphere, that would be tough. But actually just I think Robin's idea of silica aerogel to make farms on Mars, because there's plenty of carbon dioxide on Mars for photosynthesis. If you just warm things up enough and you've got water. Robin's idea of terraforming the surface of Mars, the surface layer of Mars with silica aerogel is actually possible. If you build a colony on Mars, people might be using that to grow crops instead of actually just building domes. So people will still have to live on domes until you find a way to just bring a whole lot, like thousands of comets worth of nitrogen onto Mars. Once you get enough atmosphere there, you can make CO2, you can make oxygen by photosynthesis or solar energy. But you just getting the surface pressure up to where you have a conceivably breathable atmosphere, short sleeve atmosphere, that will be tough with technology we've got in the foreseeable future. Because you can't just cook that out of the rocks. There's just not enough volatiles there.
Great. So I propose we conclude here.